Okay. This evening we are going to cover chapter 3, which is Polygon Triangulation, and the motivating problem is guarding an art gallery. Again, this chapter is composed of 3 parts. The first part is how we can solve the art gallery problem by modeling it as putting cameras in triangles. So the first part is to devise a solution for the art gallery problem. And then the next step is, this one requires a triangulation of a polygon. So the next next 2 parts in this chapter are about how to triangulate a given simple polygon in 2 steps. First, by turning it into a y-monotone polygon, and then triangulating y-monotone polygon in linear time easily by using a stack. Okay, so I'm going to talk about all those 3 parts today. And we also have a set of slides. So this is week 4, and we are right on schedule on the course web page. So this is week of November 2nd. We are exactly here, week 4, and we are talking about polygon triangulation, which is chapter 3 from the textbook. And we, from this time forward, we have lecture slides that I got from and the Mirzayan's slides from his course. These are subsets of those slides that he uses. So let me download these slides, and we will also, in addition to the book, material in the book, we're also going to use these slides. So it's here. Okay, so yeah, the slides are by Andy Mirzayan, and the subset of the original slides are used here. And as usual, if you have any questions, any part that you don't follow, understand, please feel free to write in the chat box. And also, you may unmute yourself and speak up, speak your question to the microphone. Okay, so the motivating problem of this chapter is called guarding an art gallery. And the problem is an optimization problem, actually, in addition to being a geometric problem. It's also an optimization problem. We are given a simple polygon. A simple polygon is defined in such a way that it's the area of the polygon, the entire area of the polygon is a connected region in which no 2 edges intersect with itself. There are no holes in it. So just think about any concave polygon. Convex polygons are very trivial to solve for this problem. We just need 1 camera to guard the entire convex polygon, so we are not going to consider them in this chapter. We will have concave polygons. So this is like a single simple polygon. If you count the vertices, again, when we are given a simple polygon, it's going to be given to us as an ordered set of vertices in counterclockwise order. For example, this is V1, V2, V3, V4, V5, 6, 7, 8, 9, 10, 11. So it goes like this. Maybe this is like a 25 gon or something. I don't know how many vertices it has, but this is a polygon. And our goal will be to put cameras. So this is like the floor map of an art gallery. It will be given to us as a 2D polygon. And our goal will be to put cameras, to place cameras in the interior of this polygon such that the entire interior of the polygon is covered by the union of these cameras. And a camera will be able to see 360 degrees around itself. So if there's a line of sight from the camera position to any point on the polygon, which means that the line of sight is defined like this. If you can draw a line segment from that camera position to a point inside the polygon, and this line segment is entirely inside the polygon, then there is a line of sight from this point, from the camera to that point, and that point is seen by this camera. So the yellow region that you see here is the entire set of points which this camera sees. As you can see, the camera cannot see a point here, because when we connect the camera position to that point, as you can see, it intersect one of the or actually two of the polygon edges. Therefore, there is no line of sight from the camera to that point, so it's not seen by the camera. So our goal is to cover the entire floor plan with a minimum number of cameras as possible. So the problem is also, as I said, I mean, you can guard the entire polygon trivially by placing a camera at every vertex. That's what you can do. For example, you can say, okay, if I have an n-gon, let's place n cameras at every vertex. This sure will cover the entire polygon. So that's a trivial solution. But our goal is not only to cover, but to do this with minimum number of cameras as possible. And in this chapter, we will not be solving this minimization problem because the minimization problem itself is NP hard. So finding the minimum number of cameras is a difficult problem. Nobody has found a solution to solve this problem in practical amount of time. But what we can do is we can at least have a strategy in which we need much less than n cameras. We are going to first, in the first part of this chapter, we are going to prove an upper bound. It's like a tight upper bound in the sense that there are certain polygons which require that many cameras. That upper bound is going to be the floor of n over 3. I'm going to be writing it in chat box. So this floor of n divided by 3 is the upper bound we are going to prove first. It means that upper bound means that for simple polygons, the floor n over 3, if you have an n-gon, if you have a simple polygon with n vertices, you will never need more than floor of n over 3 cameras. So there's a solution with with at most this many cameras guarding the entire gallery. And there are some polygons which actually require this many cameras. Okay, there's an example of that in the book too. I'm going to talk about that. But this is in the first part, we are going to prove this upper bound on the number of triangles. So for example, if a company comes and says that, okay, this is your gallery, you have to purchase n over 2 cameras to guard the entire polygon, you should not believe in that company because probably they are trying to sell you more cameras than they are needed because it's possible to do that in n over 3 cameras, not n over 2. Okay, so but as I said, this is an upper bound. For certain polygons, the actual minimum number of polygons may be smaller than this number. So you may ask yourself, okay, if this is an NP hard problem, then how can we have this n over 3 as the solution? It's not the solution actually. The actual minimum number of polygons in a number of cameras in some polygons can be even smaller than this. But finding the smaller number is difficult. This is what NP hardness states. For certain polygons, this floor, you may even need smaller cameras, smaller number of cameras than floor of n over 3, but you will never need more than this many cameras. Floor of n over 3 is an upper bound, okay? And it's like a tight upper bound in such a way that some polygons actually need this many cameras. All right, so that's the first part we are going to talk about. Then the solution, this upper bound actually, floor of n over 3, comes from triangulation of the simple polygon into triangles. So the solution that we are going to work on first is let's divide this entire polygon into triangles. And by using these triangles, place the cameras in a clever way. We are going to first prove how many triangles will there be. So let's ask this question. If you have an n-gon, if I have an n-gon like this, if I want to divide, a simple polygon with n vertices, if I triangulate this such that the inner parts are all composed of triangles, okay? And I will do that by drawing diagonals from vertices to vertices, and a diagonal will be a line segment which is also entirely inside the polygon. So for example, I will not be able to draw a diagonal from this vertex to this vertex because it will not be a valid diagonal. So by drawing diagonals, we will create triangles. The first proof in that we'll see is if you have an n-gon, there are exactly n-2 triangles. So for any n-gon, the triangulation will result in exactly n-2 triangles. And with these n-2 triangles, for example, since each of them is complex, each of them is a convex polygon, you can place one camera in one triangle, but this is not very optimal. If you are going to see, it will again give you n-2 triangles, which is not a good upper bound. We will actually be using neighborhoods of triangles to place the cameras in strategic locations to guard the entire gallery with n/3 cameras. Okay, so let's start. So this is actually repeating what I already said, but let's see what if I'm missing anything. So this problem first was proposed by Victor Klee in 1973. So it's a very old problem, the art gallery problem. And it's, as I told you, it's NP hard to determine the minimum number of camera guards for an arbitrary given simple polygon. And this NP hardness actually was proven 11 years later than the problem was stated. So if we have a polygon with n vertices, if P is convex, this is the trivial case, any camera that you place anywhere inside the polygon is going to see the entire interior of the polygon. This is by the definition of the convexity. So a single camera will be sufficient. So this is this trivial case. We are not interested in this. So this is also the trivial solution. N guards, if we place n cameras at every vertex, this is going to be also sufficient. But can we use less than n cameras? This is what we try to do in this chapter. So I'm skipping this three-dimensional polytopes, meaning that, I mean, if in 3 dimensions, this may not be the case. But we're not going to be looking at three-dimensional problems in this course, so I'm skipping this statement. Yeah, triangle with if we triangulate the given polygon P, we will be able to actually use less than exactly floor n/3 cameras will be sufficient to guard the entire polygon. So this is a simple polygon, as you can see, and the triangulation of simple polygon P is this. There are many triangulations possible. A triangulation of a polygon is not unique. Okay, that's another thing. We could have obtained a different triangulation by drawing different diagonals between different vertex pairs. So a triangulation is not unique. That's one thing you should know. But what is unique about these triangulations is that any triangulation of P will exactly have n-2 triangles in it. And the proof of this could be done by induction. Okay, let me just now, I'm going to prove, first I'm going to now prove that any triangulation contains n-2 triangles in it, and I'm going to prove this by induction. I'm going to use my blackboard, this GIMP. So let's have a polygon, some arbitrary simple polygon like this. Okay, now, so there are vertices here. Actually, I could have drawn a better one to, actually, let's have this polygon, okay? Now, the proof by induction is going to be like this. We will first start, our base case is when n is equal to 3, okay? When you have a triangle, how many triangles are there? The number of triangles is equal to 1, which is equal to 3 minus 2, right? So it's the number of triangles holds for the base case. If you have a triangle with 3 vertices, and since I'm trying to prove the number of triangles is equal to n minus 2, which is equal to 3 minus 2, for a triangle, there is 1 triangle. All right, so this is our base case. Now, assume that for some arbitrary large angon n, all the numbers less than n, for all the vertices, for all the polygons less than n, this holds true. This is our inductive hypothesis. For polygons with less than n vertices, we know that, for example, if they contain m vertices, for all m less than m, the number of triangles such an m-gon contains is m minus 2. So we know this is our inductive hypothesis. Now, by knowing this, can we prove that any n-gon will have exactly n minus 2 triangles? And the proof is actually by drawing a diagonal, and by actually first showing that it's always possible to draw a diagonal in any n-gon in which n is greater than 3. Okay, if you have a polygon with more than 3 vertices, it's always possible to draw a diagonal in it, which will split the polygon into 2 pieces. And the diagonal, drawing a diagonal for sure is this. The algorithm is this. Find the leftmost vertex. Okay, we go to the leftmost vertex of the polygon and we look at the neighboring edges. Actually, we have a nice, better figure in the book. Let me just use that one instead of this. I'm just going to be using the one in the book. Oops, where is the book? The book is here. Yeah, this is the book. Yeah, the both of them are very good figures. And shows the 2 possible cases that we can have. So the first case is simple. So let's let V be the leftmost vertex. Okay. Now what we do is basically we look at the 2 other vertices in which V is adjacent to, W and U. Okay. So if there is no other vertex closer to V, to the left of this UV, if there is no vertex in the polygon to the left of UV, then this is a diagonal that we can always draw. Okay, so there are 2 cases where there is no vertex to the left of the line segment connecting UV. In that case, UV is a valid diagonal which will split off a triangle from the remainder of the polygon. Or it may be the case that, look at this one, U and W, there are actually 2 vertices, V prime and let's call the other one V double prime, to the left of UV. Okay, now there are 2 vertices here to the left of UW, and therefore we cannot safely draw this diagonal. UW is not always a safe diagonal, but if that's the case, if there are some vertices to the left of UW, let's pick the one which is farthest away from UW. So let's V prime be that one in this figure. That's the one that is farthest away from UW. Okay, that's V prime. Now we clearly see that since there are no other vertices, since V prime is the farthest vertex away from UW, and V was the leftmost vertex, there can never be, by the definition of this V prime, there can be no other vertex to the left of this. And we know that this here is the interior of the polygon. So therefore, we can safely draw a diagonal between V and V prime. So this, in either of these 2 cases, we can draw a diagonal. All right, drawing a diagonal splits the polygon into 2 parts. Not necessarily, for example, if you draw this diagonal, for example, one of the polygons, if you draw this V prime diagonal, one of the polygons is a quadrilateral or a polygon with 4 vertices, 1, 2, 3, 4. The other is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The other is a 12th cone, okay? And this one is a quadrilateral for 4 vertices. Now, what I mean is that we do not always get a triangle out of this, but with drawing this diagonal, we draw it into 2 smaller polygons. Hence, gives us chopping this polygon into 2 smaller polygons gives us a chance to, sorry, not this one, to use the inductive hypothesis. So this is where we are going to use the inductive hypothesis. For example, if let's assume I drove this diagonal, not using the technique that is described in the book, just assume that I draw a diagonal here. Okay, now look at this part of the polygon. It contains M1 vertices. The right polygon contains M2 vertices, and since it's the larger polygon is chopped into 2 smaller polygons, both M1 and M2, what are they? They are smaller than N, right? Hence, the number of triangles in this part is exactly M2 minus 2, and the number of triangles in this part is M1 minus 2. Okay, so these are the number of triangles here and number of triangles here. Now, so the total number of triangles in the entire polygon will be equal to M1 minus 2 plus M2 minus 2, right? So this is the total number of triangles in both of the polygons. Now, can I write M1 plus M2 in terms of N? What is the relationship between M1, M2, and N? So can I get rid of M1 and M2 here and write them in terms of N? Let's look at what M1 is, and let's look at what M2 is. And can you write in the chat box what is N equal to in terms of M1 and M2? I'm waiting for your answers. Exactly, yeah. So M1 plus M2 minus 2 is equal to N, because these 2 vertices at the diagonal, they are counted both in M1 and both in M2, right? So if you add them up and subtract 2 from this, you will get N. In other words, N is equal to M1 plus M2 minus 2, right? So if I replace this part with N, what do I get? N minus 2 is the number of triangles. All right, so this one, this concludes the proof. So with proof by induction, we have proven that any simple polygon, when it's triangulated, is going to contain exactly N minus 2 triangles. All right, when we have the triangles, how can we use them to solve the art gallery problem? That's the next thing. So let's see on the slides how they're covered. So yeah, this is a triangulation. Also, there is the dual of a triangulation. If imagine for each triangle, let's imagine we construct a graph in which every triangle is a node in this graph. In other words, I will have a graph with exactly N minus 2 nodes. Okay, let's have a graph with N minus 2 nodes. And any 2 nodes will be connected by an edge if these 2 triangles share a diagonal. I will get this graph at the end. Look at this graph. This is, as you can see, every triangle is represented by a node in this graph. And if they share a diagonal, there's an edge between them. This is for a simple polygon, this dual graph of this triangulation will always be a tree. Okay, and hence it's called dual tree of the triangulation. There will exactly be, because N minus 3 edges, N minus 3 diagonals here. We can also prove that actually. And now what happens is that with these N minus 3 diagonals, we will always have a tree. But if it was not a simple polygon, for example, if you have a polygon with a hole in it, the dual tree may actually be may contain a cycle, which means that it will not be a tree. But in our case, for simple polygons, the dual the dual graph of this triangulation will always be a tree, hence it's called dual tree. Now, yeah, this one is the proof for n-2 triangles for any polygon. Okay, and yeah, any polygon, any simple n-gon admits at least one triangulation. Such a triangulation can be computed in n squared time. We will actually see an algorithm today to compute this in n log n time, and any triangulation has n-2 triangles. This is what we have proven by induction, so I'm skipping this slide as well. Now, actually, this one uses the solution that I'm going to display next, so it skips some important parts from the book, so I'm going to follow the book in that regard. Okay, so after this, what we are going to do is, when we have the triangulation, we are going to place the cameras in strategic location in such a way that, for example, we will not need more than n/3 cameras. So what are these strategic locations? Let's see. Look at this triangulation. The vertices are colored with 3 different colors: black, gray, or white. Okay, and every triangle has one of these 3 colors. This is called the 3 coloring of a triangulation. Okay, and what we are going to do is, we see that a gray here sees 2 triangles, and this gray sees this one, many of them. Okay, and since I have the number of triangles n-2, the number of a coloring group is exactly, it cannot be larger than the floor of n over, actually the smallest of those color groups will be floor of n/3. So and it's going to be like this. The strategy we are going to, we can start at any triangle, start with any triangle, and color its vertices with the 3 different colors. And you're going to go to the next neighboring triangle by following this dual tree, by following the neighboring triangle which shares a diagonal with it. The next vertex will be already given, because this triangle is colored by 3 colors. Since this one is gray, this one is white, the only remaining color for this triangle vertex is black. So this, I forgot to mention that maybe. In this 3 coloring problem, every triangle's vertices will be colored by 3 different colors, okay? Given a triangle, we cannot have 2 of the same colors at the vertices of that triangle. Each of them may be of different colors. So if starting with this triangle, and we can give arbitrary colors, if this is gray and white, then this is for sure, it must be black. Then if this is white and black, then this must be gray. And we have gray and black here, then this must be white. Okay, if this is white and black, then this must be gray. So by following, actually using this dual graph by depth first traversal of the dual tree, we can start with an arbitrary node here. For that arbitrary node, we color the triangle with arbitrary colors. We will follow the next triangle by traversing this dual tree. We will come to the next one, and when we come to the next one, it will have one of the triangles that is visited already, one of the nodes visited, and that triangle will be sharing a single diagonal with this, and therefore these 2 colors will be determined. The remaining vertex color will be assigned with the remaining available color. And then with depth first traversal, we will go to the next triangle. We will set this color, then we will jump to next one. We will set this color, and we will jump to this one. And from here, for example, there are 2 paths to go. Either we go here and color these 2 things after depth first traversal. After we traverse the nodes here all the way to the depth. We will continue from here, and then we may come here. But depth first traversal, and this is also another important thing about this dual tree, is it's connected. Okay, so starting with an arbitrary vertex in this graph, with depth first traversal, you will be able to visit all of the triangles, all of the nodes in this dual tree, and during this visit, you will be coloring each triangle with these 3 colors. And after you have the 3 color groups, just count how many of them you have. Let's count how many blacks we have. 1, 2, 3, 4, 5, 6. The grays 1, 2, 3, 4, 5, 6, 7, and the whites 1, 2, 3, 4, 5, 6. So we have 6, 6, and 7 of these different colors, which means that pick the smallest one of those values. So their summation is 19. So 19 divided by 3, its floor is 6. So floor of 19 divided by 3 is 6. So we only need 6 cameras. You can either pick the black ones or the white ones. If you just place the cameras on the blacks, you will be covering the entire polygon by just placing the cameras on the blacks. Because how do you guarantee this again? How do you prove that placing on the blacks will be sufficient? Because every triangle has a black color, right? Is there a triangle in this polygon which doesn't have one of these colors? Is it possible? No, right? We only have 3 colors. Since each triangle's vertices should be composed of 3 different colors, then every triangle should have one of the colors, right? If every triangle has one of the colors, it means that if you assign a camera to a certain color, every one of those triangles will have that colored vertex in themselves, which means that we cover the entire polygon. Okay, so this is the first part of this chapter, and it uses this 3 coloration of the triangulation of a polygon to show that we only need n/3 floor of n/3 cameras to guard the entire simple polygon. So it's a nice proof, it's a nice finding, and the algorithm is nice. Now it leaves us with this problem though. Given a simple polygon, how are we going to triangulate it? Is there a fast way to triangulate the simple polygon? We can actually use the drawing a diagonal technique that we have used in the proof by induction of this n-2 triangles in an angon, right? So given an angon, it tells you how to iteratively draw a diagonal. You can apply the same technique with the remaining polygons until they have only 3 vertices left. But this algorithm is not so efficient. It gives us an n-square or n-square technique, because in order to find the leftmost vertex and then finding whether there's any vertex to the left of this edge, diagonal or line segment connecting U and W, takes linear time. We can find this V prime in linear time. But since we have to draw this diagonal n-3 times, n-3 times n gives us a quadratic running time algorithm. So we can actually, this gives us an algorithm which is O(n) square time. We can draw these diagonals repeatedly until all we have left are triangles. So this is one way to triangulate a given polygon. But this is an O(n) square algorithm. So in the next 2 sections, we are going to see an n log n algorithm to solve this problem. Given a simple polygon divided into triangular pieces in n log n time. Okay, so that's this. So all right, let's go back to the slides. So this figure on top here, this like hairy comb that you see here, is a polygon that shows that floor of n/3 is sometimes necessary for a polygon. So it's a good upper bound. It's a tight upper bound in such a way that certain polygons like these, if you have a polygon like this with triangular prongs coming out of them, you can actually you actually need n/3 cameras placed at these strategic locations. And here are some polygon triangulation algorithms. Oh, this diagonal that we were drawing to the leftmost vertex is sometimes called ear removal, because we are removing the leftmost ear of a polygon. So we are chopping off leftmost triangles from the polygon, which is O(n) squared time. It was actually due to Lenz, and it was an algorithm in 1911. So polygon triangulation, unlike the art gallery problem, is actually an older problem. And we are going to see a plane sweep algorithm today in this chapter, and it's by Gary, Johnson, Preparat, and Tarian, and it was developed in 1978. So the algorithm we are going to see today is a very old algorithm. And there are some other variations of it in n-log n time. There is a linear time algorithm that actually triangulates polygons in linear time. We are not going to cover this in this course, but just to show you that it's possible to even have faster algorithms. There's a linear randomized algorithm that was proposed in 2000. Okay, so the algorithm you're going to see by Gary, Jensen, Preparat, and Tarian is composed of two parts. Now we are in the book. We are now jumping to section 2. Okay, so here partitioning a polygon into monotone pieces. That's the first part. And after we have a monotone polygon, you'll see that it's very simple to triangulate a monotone polygon in linear time. A monotone polygon is a polygon like this. Actually, a monotone polygon is monotone with respect to some line L. If that line L is the y-axis, we call such polygons y-monotone. So I'm writing it in the chat box. So y-monotone polygons are polygons in which if we drove a line that is perpendicular to the y-axis, or that is parallel to the x-axis, you may think about it like this. So if you draw a line like this anywhere, any line parallel to the x-axis, it will intersect the polygon in a connected segment, either at a single line segment like this, or either at a single point, or maybe at an entire line. Okay, so the interior of the polygon will be a single segment, single connected part. That makes it y-monotone. So this one, for example, is not y-monotone. If I draw a horizontal line just below this vertex V, as you can see, this line intersects the polygon in two segments. One is here, the other is here. So if there are more than one segments the line is intersecting, it's not called y-monotone. It's going to be monotone if the intersection is just one region. Another way to look at y-monotone polygon is considering the top vertex. Okay, from the top vertex, there are two chains. One of them is the left chain, the other is the right chain. If you follow the vertices on the left chain, their y coordinates are non-increasing, all right? Meaning that they either decrease or they stay the same. So that's a property of y-monotone polygons. So if you start walking from the top vertex, you're always going down. You may stay at the same level. It doesn't actually it doesn't break the monotonicity rule, but they either decrease or stay the same. Here, as you can see, at this vertex V, we have not actually vertex V. They are decreasing. At this vertex here, we have a problem. This is also a problematic vertex, right? I mean, we come here, decrease, and suddenly we see an increase. Okay, so this is also a problematic vertex. So yeah, our goal will be to, given a simple polygon, to turn them into y-monotone polygons first. This will be the first thing that we are going to do, and we will be using a plane sweep algorithm, just like as in chapter 2. We will be using a plane sweep algorithm to do that. But first, we need to analyze how can we make a simple polygon, like this, for example, a monotone polygon. We see that the way to make a polygon monotone is to divide it into smaller polygons. So we are going to chop this polygon into pieces, in which each piece is going to be y-monotone in itself. And we will do this by drawing diagonals, just like in triangulation. But this is what we will do. This will be simpler than triangulation, and our goal will be just to get rid of vertices that is bad for monotonicity. So therefore, we define a certain types of vertices. Here is a really nice figure, okay, which classifies each vertex of a polygon into one of the 5 vertex categories. Okay, there will be a regular. Let's first start with the simplest one. A regular vertex, it'll be a vertex in which one of the vertex is above, the other vertex is below. So in other words, when you're going through a regular vertex, monotonicity is not broken. So your one of your neighbors is above you, the other is below you. So when the polygon is going through you towards the edges, using the edges, the y-coordinate is decreasing, therefore, or increasing. Okay, in this case, if you're walking this way, so V2 is also a regular vertex here. V7 is regular, V6 is regular, V10 is regular. The two neighboring the two adjacent vertices are on 2 different parts. One of them is above, the other is below. Such vertices are called regular vertices. Now, all the others are called actually turn vertices. The remaining 4 categories, start, end, split, merge, they are also all categorized together as turn vertices. But some of these turn vertices are bad, especially split and merge vertices. Now let's first start again with the ones that are not bad in terms of monotonicity. A start vertex is a vertex in which both of the neighbors are below it. Okay, like look at V5. V4 and V6 are both below, and their y-coordinates are smaller than the y-coordinate of V5. By the way, if 2 vertices have the same y-coordinate, we are going to consider the one to the right as the vertex that is below. Okay, so if 2 vertices have the same y-coordinate, you will consider this one on the right to be the vertex that is below. Now, I mean, this is a degenerate case we can talk about later. So for understanding the algorithm, let's assume that no 2 vertices have the same y-coordinate, okay, for simplicity. So if you look at V5, it's both of the vertices are below it. And if the interior of the polygon, if the angle we make at the interior of the polygon is less than 180 degrees, then this vertex is called a start vertex. In other words, it's a local top vertex. A start vertex is locally top of the polygon. Okay, the polygon is below it. Okay, so for example, if you see a similar vertex in which, for example, look at V14. V14 and V5 share the same thing in terms of their neighbors. For V14, the neighbors are also below V14, right? Both neighbors are below V14. But V14 and V5 are classified differently because V14 is not like a top vertex of a polygon because the interior of the polygon is not here. The interior of the polygon actually has more than 180 degrees here. It's actually locally above V14. All right, so we call V14 split vertex because if you consider, let me just copy this. Let me zoom in once more. and copy this. Oh, well, how did I think we were doing it like this? Yeah. Let me copy this area into GIMP, and I will be able to draw with different colors on it. All right, let's get a new one. Let's copy this one on it. Yeah. And let's flatten the image. All right, now I will be able to draw on this with different colors. How can I change the color? Oh, maybe the color is somewhere here. Oh yeah, here. Actually, it's the color panel is somehow behind. Oh, it's right here. Let me just get these. Yeah, now I'm able to move it here. Okay, so let's choose a red color. All right, now if you look at this V14, the angle that it makes with the interior is greater than 180 degrees. All right, therefore V5 is called a split vertex. Why it's called a split vertex? Because imagine a sweep line that is going down. Okay, imagine a sweep line and imagine this V14 as the event point. And here the interior of the polygon, just consider the interior of the polygon just above the sweep line L and just below this event point V14. So consider the interior of the polygon. The interior of the polygon that we intersect is just connected. It's just one piece, right? And after here, after this event point V14, what happened? The interior of the polygon now is in two pieces, okay? Now the interior of the polygon is split into two pieces, hence just after V14. Therefore, V14 is called a split vertex. Again, the rule is if two neighbors are below it, and the interior of the polygon is 180 degrees, more than 180 degrees, it's a split vertex. And this is a start vertex if the interior of the polygon is less than 180 degrees. And the AND vertex and merge vertex are similar. For AND and merge vertices, their neighbors, both of their neighbors have y coordinates larger than themselves. Okay, so V13 is such a vertex, and if the interior of the polygon again is less than 180 degrees, it's like a local minima. It's like the locally ending vertex of a polygon, hence it's called the AND vertex. If you look at this one, V8, again V8 is like a local minima, but the polygon does not end here because the polygon locally is below this vertex. It was here, it was above, and the interior angle is greater than 180 degrees, and this V8 is called a merge vertex. And again, the naming is intuitive. The two disconnected parts here and here that was above the sweep line actually merges and becomes a single connected component. Our sweep line intersects the entire polygon in a single connected region, and the two regions are merged at that merge vertex. Okay, now here is the thing. There's a theorem in the book, or maybe it's a lemma, that states that if a polygon does not contain any merge or split vertex, okay? If a polygon does not have any split or merge vertex, then it's a y-monotone polygon. Okay, so the algorithms that we are going to develop will be trying to get rid of the split and merge vertices by drawing diagonals. So if we don't have any split and merge vertex, then we have a y-monotone polygon, so our goal will be to get rid of them. And here is the proof in the book about this. I'm just going to show you the figure. So this is the proof that shows that if there is a polygon which is not y-monotone, there has to be either a split vertex or a merge vertex. Okay, So it shows like this. If imagine there's a line, it intersects it in two regions. Let PQ be the leftmost region. So in order to be not y-monotone, there has to be another region our line intersects, right? We cannot intersect with just single region. Just pick this line in such a way that the y-monotonicity breaks. There are two regions our line intersects with. Now follow the polygon's edges until you intersect with this line again. And since the interior of the polygon remains here, there must be a split vertex. And if you follow again, and sometimes when you follow it, you may get to some place else, and in that case, it will be a merge vertex. Okay, so there should be either a split vertex or a merge vertex for you to be able to intersect with the polygon interior again. So this is how it is proven in the book. So our goal will be to get rid of them. How can we get rid of split or merge vertices? By drawing diagonals. Imagine, so here's what we're going to do. Let me get the same one. Can I copy it again? Great. Flatten. And we're going to have a 15-minute break just after this, just after I indicate what kind of things we can draw. So look at this merge vertex. V8 was a merge vertex. So one neighbor here is above, the other is also above. If I can draw a diagonal from this merge vertex to some other vertex that is below it, okay, what will happen is that this neighbor is going to be above, this neighbor is going to be below, right? I mean, if you can draw a diagonal to some vertex that lies below the sweep line, this vertex V8 turns into a regular vertex. Actually, it will be difficult in our plane sweep algorithm because merge vertices, I mean, because we don't know anything below the sweep line, right? But we will see how we can get rid of merge vertices when we come to an event point that is below it. It's easier to get rid of split vertices in our plane sweep algorithm. The same is true for split vertices. Both of its neighbors are below. If we can draw a diagonal to any of the vertices above, if we can draw a valid diagonal from the split vertex to some vertex that is above the sweep line, what happens is that one neighbor becomes above, the other neighbor was below, so it becomes a regular vertex. So this is how we're going to make the polygon monotone, by drawing diagonals. For split vertices, we are going to draw diagonals to a vertex that is above them. And for merge vertices, we are going to draw a diagonal to some vertices that are below them. Okay, so, and we will do it by a plane sweep algorithm. So let's have a 15-minute break now, a little bit more than 15 minutes. So let's meet again at 10 past 7, all right? 10 past 7, we're going to meet, and I'm going to finish in about an hour. The rest of the chapter will take about an hour to finish, all right? Let's see you all in 10 past 7. I'm going to stop the recording now.